Hello everyone and welcome to this video about angular velocity of a moving point. So this is the very basic concept from which rigid body motion sort of begins, and if we can understand this we will be in a good situation to understand rigid body motion in a very fundamental and good way. Right, so let us jump ahead into the definition of angular velocity. How this angular velocity is basically defined. So, the most basic form of angular velocity is where there is a point O which is fixed and there is a point P which is moving in a circular path around this first point O. Right? So, in this situation, the distance between them remains fixed. So, these three conditions are being met, that the point O is at rest, point P moves in a circular path, and the second point basically leads us to the third one, that the distance is constant. Then we can say that what exactly is rotating. So we are all kind of familiar with the physical sense of rotation of an object. So in this situation, what exactly is rotating? So we can definitely say that the line segment OP, so this line segment OP will keep changing orientation like this. So we can say that it is rotating. We get the physical sense, physical idea of rotation from it. Uh, or we can, in more technical terms, we can say that the line segment OP changes orientation. So if we take the orientation of this line segment at two different time instants, as shown here in this diagram, uh, so this is the orientation at one instant, this is the orientation at some other instant. It is clear that there is an angle between them. An angle is formed between them, and that angle is non-zero. So this is the meaning of rotation, that if a line segment changes orientation such that between its two orientations there is an angle which is non-zero, that is in fact the very definition of changing orientation. Uh, then we can say that there is some kind of angular displacement, there is some kind of rotation taking place. That line segment is undergoing rotation, it is changing orientation. All these terms mean the same thing. And then this angle can be termed as the angular displacement. And by this definition of the angular displacement of the line segment, we can also say that theta is the angular displacement of P about the stationary center O, about this point O. So these are some basic definitions. Then we can say, we come to angular velocity. Angular velocity will then be the rate at which this angle theta changes. So this angle theta will change, it will grow as the point P moves. So as the point P moves around in a circle like this line segment will keep changing orientation. So from its initial position, this angle will keep growing, and the time rate at which this angle grows is the angular velocity. So that is why the terms are chosen like this. It makes perfect sense to call the rate of change of angular displacement as angular velocity. And we can have a mathematical treatment of this fact that we have just seen, that the rate at which this angular displacement changes will be d theta by dt. So in an infinitesimal time interval, the point P has an angular displacement d theta. This angular displacement is d theta, which is a very small angle, and the radius in which the point P moves is r, and the arc length that it moves in this time is dl. So we can have this simple well-known relation, dl equal to r d theta. And if we divide by dt on both sides, so on the left side we get the speed of the particle, which is the arc length traveled in time dt. The arc length dl over time dt is the is the speed of the particle, is the linear speed of the particle, and d theta by dt is the angular velocity, which we have just seen, which we have just defined. So angular velocity is a new thing right now for us. We have defined this. We have defined it as the rate of change of an angular displacement of a point when it is moving in a circular path. This is the simplest definition of angular velocity. And using this calculation, we reach this relation that the linear speed is radius times angular velocity, which is quite well known. And therefore, we can invert this relation and form this relation, which is omega equal to v by r. And from this, we get the mathematical definition of angular velocity, which says that if a point, so I'll draw the diagram here again, if a point P moves around another point in a circular path and the radius of that circle is r and the speed of the particle is v, then the instantaneous angular velocity of P about O is v by r. Now this angular velocity can change from instant to instant. It is instantaneous. So it is instantaneous angular velocity, right? Velocity of P over distance OP. Now in this example, we have kept distance OP as constant, but distance OP can be varying as well. But we will discuss that later. Let us now focus on the case where distance OP is fixed. And the velocity of P, which is in the numerator, can also be either changing or constant. So it can be uniform circular motion, or it can be non-uniform circular motion where the linear speed is changing. If the linear speed is changing, then in the numerator, then the angular velocity will change. So this is instantaneous angular velocity. This thing that I've put in the box over here is instantaneous angular velocity. And with magnitude, it also has a direction. So there can be two ways of rotation, and we call those two ways of rotation as clockwise or anti-clockwise. So we are only talking about point moving in a plane. Point is never leaving its plane. So in this planar motion, there can be two simple directions in which that rotation can take place. So if this is OP is changing orientation like this, it could have also changed orientation in the opposite direction. So these are clearly two different ways of rotation, and there is no other way. These two are the only directions or the only ways in which the point P can rotate about O, right? So you can check this, you can play with this, and you will realize that there are no other ways possible for P to rotate, P to go about in a circle around O. There are only two ways, and one we call clockwise and the other anti-clockwise, because of course clockwise motion is exactly like the hands of a clock. The hands of a clock go in this direction, right? And anti-clockwise is the opposite. So angular velocity has a magnitude, which I detailed over here in this box, and it has a direction. So now let us go to the case if O is also moving. If the point O is also moving, then also we can define the angular velocity in exactly the same way. Let us now jump into this case. What is this case exactly? So there is a point O and there is a point P. Both are moving, but they are moving in a particular way such that their velocities are such at every instant such that the distance OP remains constant, right? So so this is a diagram of a particular instant. So this is at a particular instant. So at a particular instant, the point O and the point P both have velocities. So I've shown this as vectors VO and VP, right? They're both moving, so they both have velocities. Now we resolve these velocities. So this is a very critical, very important point, very important concept in rotation. This is one of the most, if not the most fundamental concept of rigid body motion. This concept of resolving the velocities of these two moving points along two directions. And what are these directions? The first direction is along OP and the second is perpendicular to OP. So this VO is resolved perpendicular to OP and parallel to OP. So this is the line OP and this is an instantaneous line. So this, as O moves, let's say after some time O is here, P is here, so OP will change orientation, OP will change. So that is why I'm stressing the point that we are looking at this picture at a particular instant, and everything that we talk about will be related to this particular instant. This is a very important point and you should hold on to it, that everything we will talk in this discussion now will be related to this particular instant, right? So at this particular instant, OP is in this particular direction. This is the line segment OP currently. So this is the direction along OP and this is the direction perpendicular to OP. So I resolve these velocities in these two particular directions. I do that for both VO and VP, and I call these components VO parallel, VO perpendicular, VP parallel and VP perpendicular. So let's move on what we want to do with these components. So since OP remains fixed, this is something that you might be able to understand very simply, that since OP remains fixed, so in a particular infinitesimal time interval after this instant, the distance OP should not change, because the distance OP never changes. So in the time dt after this instant, the distance OP should not change, and therefore the displacements, so I will write it here, since OP remains fixed, displacements parallel to OP must be equal during dt. So in the next time interval after this instant dt, in that interval is called dt, the displacements along OP should be equal and in the same direction as well. So if let's say during this short interval dt, the point, let me show here in a separate diagram. So let's say this is O and this is P. In the short interval, let's say O moves slightly in this direction, P moves slightly in this direction. Then the distance OP has clearly changed in the time dt, right? But if they move in the same direction and by the same amount, so if O and P move in the same direction by the same amount, or they don't move at all along OP, then the distance OP remains fixed. So this idea is quite simple, that distance OP will remain a fixed distance if at this instant velocities of O and P parallel to OP are equal. They are equal in direction as well as magnitude. Very important point. So this is a condition that we get. This is a condition that we get because we have already assumed that OP remains fixed. So we get this condition, this relation between the two components, two parallel components of the velocity. Now let us go into the frame of O. What we mean, the frame of O is that what the particle O is seeing. So if there is an observer at O, what is it seeing? So I'm just I'm just applying the basic concept of relative velocity, which you all should know if you're watching this video, that Vp relative to O. So this notation means velocity of P relative to O is VO minus Vp. Right? So this is the picture that O sees. So let us go back to this. Let us compare these two diagrams. So this is VO perpendicular, this one over here, and this is VP perpendicular. The parallel components are already equal. So when we subtract the velocity of P from O, we subtract the parallel and perpendicular components separately, right? We can do that. So we can write it over here. So this is, I'll write it in short. I'll write it quickly because it's not very difficult to understand. Right? The parallel components are and perpendicular components are subtracted separately. So the parallel components get subtracted and amount to 0. So the relative velocity is purely along the perpendicular direction. So this part becomes 0. So only the perpendicular components get subtracted and they show up as the relative velocity. So this is what we see in this diagram. This is what we see in this particular diagram, right? So this is OP and this is perpendicular to OP. So now we can say that in the frame of O, P is moving in a circular path, right? Clearly, as seen from the ground frame, this is the picture from the ground frame. This is the picture from the ground frame. P is clearly not moving in a circular path around O, right? O is moving in this direction, P is moving in this direction. For P to go around O, P should go perpendicular. For P to travel in a circular path about O, you can write this down. For P to move around in a circular path around O, it has to travel perpendicular to the line OP, purely perpendicular to the line OP. So as seen from the ground frame, P is not moving in a circular path around O, because O is also moving, P is also moving, they're moving in random directions. But if we take this condition that OP remains fixed, then from the frame of O, so I have written it over here. So from O's perspective, as seen by O, P moves in a circular path about it and hence will have an angular velocity attached to it. So whenever a particle moves around in a circular path, we go back to the initial definition that we have defined in the beginning of the video, that the simplest condition for a particle having an angular velocity, the situation in which angular velocity is first defined, that situation is where a point is fixed, which is O, and a point P is moving in a circular path around the first point. So in this particular general situation, as seen from the ground frame, that angular velocity cannot be seen because that circular motion cannot be seen. That circular motion is not there as seen from the ground frame. But as soon as we enter the frame of O, again we see a circular motion happening. P is moving around O in a circular path. I hope you can all see this. That P is moving around O in a circular path and therefore will have an angular velocity. This will all work out if we go into the frame of O. So, this we define as something slightly new, which is angular velocity of P in the frame of O. Earlier, the definition was that was some kind of absolute angular velocity because we were seeing it from the ground frame, from the laboratory frame. Right? Now we are looking at things from frame of O. So angular velocity of P in the frame of O about O. So one more thing that I should have added in the beginning as well, that this angular velocity of P, we call it the angular velocity about the point O. We also add this qualifier, we add this two words about O, that angular velocity of P about O. So this time it is angular velocity of P in the frame of O and also about O. So the two facts are joined together here, that it is angular velocity in the frame of O and about O, right? And in short, it is called P's angular velocity relative to O. So again, it is defined in the same way, that angular velocity of P relative to O is component of the velocity of P relative to O and perpendicular to OP, right? So in general, so let us go back a little bit, so that I can make it absolutely clear, so that you can go back and say that we got the concept in a crystal clear manner. So in this case, the distance OP is fixed. Therefore, the velocity components of O and P parallel to OP, these two components are equal. They are equal. So if I go into the frame of O, I subtract velocity of O from P to get velocity of P in the frame of O, right? That is what we do. Which is detailed over here. When we subtract the parallel components, we get 0. So we get only the difference between the perpendicular components, and that itself is the relative velocity, right? But in general, we might also have a difference in the parallel components. We might also have a case, the most general case, where 2 points are moving and there is no constraint on their velocity. There is no constraint. This constraint is not there. So then the distance OP will also freely change, and therefore the relative velocity will also have a parallel component. Currently it only has a perpendicular component. When this condition is valid, it has only a perpendicular component. But it will also have a parallel component in general. But even then the angular velocity is defined in the same way using the perpendicular component. So what I mean is that in the general case, as seen from O, P will not move in a circular path. P will still not move in a circular path. Because it will have, so in this relative picture, it will have a perpendicular component, which is this, and it might also have a parallel component. So it is clearly moving in this direction, which is not a circular path. But it is still possible and valid to define the angular velocity in terms of only this perpendicular component, because essentially, and you should focus very much here because this is a very important concept, that essentially the velocity component of P relative to OP is the one which is taking it around in a circle around O, and this parallel component is not contributing to this. It's not contributing to the change of orientation of OP. So it should not feature the parallel component. This parallel component will be there and can be there, but it does not feature in the angular velocity definition because it does not change the orientation of OP. It does not contribute to the change of orientation or what we call rotation of OP, the line segment. So component of P's velocity relative to O, perpendicular to OP, if you divide only that by the distance OP, you will get the angular velocity of P relative to O. That makes sense. Right? So here I've detailed the same thing, that in general, the parallel component of velocities will not be 0. But in this case, in our special case, the parallel components are the same. So the relative velocity is exactly equal to the relative velocity component along the perpendicular direction. So in general, so this is where I've highlighted the difference between the two cases. So generally, whether OP is fixed or not, we take only the perpendicular component. But when OP is fixed, the perpendicular component and the total angular velocity are the same because the parallel component of the relative velocity is 0. So we can define, when OP is fixed, we can simply define it as like this. And finally, why are we focusing on this version of this situation where OP is fixed? Uh, is uh, because this is the most relevant uh, case for rigid body motion. And you will understand, some people might have understood already that we are already hinting towards the beginning of rigid body motion when we consider the case, when we consider the situation of 2 points moving freely, but under the constraint that the distance between them remains fixed. And in that case, we define the angular velocity. But we can also define the angular velocity in general, but we will not focus on that general definition. So we will not focus on the second definition. It does not matter to us currently, uh, and we will focus more on the simpler definition, the simpler case where OP is fixed, because that is most relevant for rigid body motion. Now finally, what if we invert the perspective? What if we go into P's perspective? It is exactly the same, because you will discover very simply that if O goes around P in a circular path, then P also goes around O in a circular path. The whole situation is invertible. O is going around in a circular path about P, as seen from P, and P is going in a circular path about O, as seen from O. And their angular velocity is also the same, and the magnitude and direction is also, but angular velocity is same in both uh, ways. The magnitude is the same, the direction is the same, so you can invert it. So I've summarized this in a particular case. So this is the situation as seen from the laboratory frame. Again, O and P are 2 points which are moving, so they have some velocity. So O will have a net velocity over here, P will also will have a net velocity in this direction. So I resolve these velocities as before along the parallel and perpendicular directions, parallel to OP and perpendicular to OP. Again, these are instantaneous pictures, instantaneous velocities, instantaneous positions of O and P, right? So if we go into the frame of O, going into the frame of O just means that velocity of O will become 0, because as seen from O, O will be at rest. But as seen from O, velocity of P will be Vp minus Vo. So we subtract both components, and again we have taken the condition here that parallel components are equal, because we are going to discuss only this part, only this condition. We are going to discuss only the case where OP is fixed from now on. So as seen from O, if you subtract the perpendicular components, you get this you get this relative velocity. And as seen from P, O also goes in a circular path, as I've said. So if you go into the frame of P, O goes around in a circular path like this. As seen from OP goes around in a circular path like this. So you can check it out on your own. It's a good exercise to apply the concept learned in this video in this particular from both sides, as seen from O and as seen from P, right? So as seen from O, if I do Vp perpendicular minus Vo perpendicular, I get this little vector, and therefore I can say that because this is perpendicular, P is moving around in a circular path, right? So one confusion that may arise over here is that there is no circular path, because we are only interested in we are only looking at an instantaneous picture. But we can understand it that if P were going around in a circular path, then at this particular instant when OP is oriented like this, P will have a velocity like this or like this. It can only have velocities in two directions. In short, we can say if P is actually going in a circular path around O, then if P is actually going around O in a circular path, then at every instant it will have a velocity which is perpendicular to OP. At every instant it will have a velocity which is perpendicular to OP. And this is guaranteed in our situation by the fact that OP is fixed. So even though we are looking at only an instant, we are guaranteed that P will go around in a circular path around O, and its velocity might change. This speed might be changing. The speed we need not hold constant. We only need the condition that OP remains fixed, and OP remains fixed guarantees that P is moving in a circular path about O, as seen at every instant. So we are only looking at a particular instant, and we are defining things from there. So if you go into O's perspective, this is the relative velocity. If you go into P's perspective, this is the relative velocity. And these two are definitely negatives of each other. They are negatives of each other. So as seen from O, P is going in a clockwise circle. As seen from P, O is also going in a clockwise circle. And their angular velocities are also the same. So V PO, which is angular velocity of P about O or relative to O, is equal to this. And similarly, you can write over here, which is the same thing. So the magnitudes are the same, the directions are the same, right? So I'm just summarizing this that if both O and P are moving, so just summarizing over here, if O and P both move relative to the lab frame such that the distance between them remains fixed, then P can be said to have an angular velocity about O. O can be said to have an angular velocity about P. And the way in which it is exactly defined is, I will underline it, angular velocity relative to O. So angular velocity relative to O encapsulates both points, that it is in the frame of O and it is about O. And we can invert the situation and we can say that O has the same angular velocity about P, or about P and in the frame of P, and we join the two facts and say relative to P. And we can also discuss the case where OP changes, even then the angular velocity is the same, even though now the points are not moving in circular paths around each other. But we can still define the angular velocities in terms of the perpendicular components of the relative velocity, as I have discussed before in this video. So as I said, we will focus only on the part of the situation where OP is fixed for now, because that is most relevant for rigid body motion. So I hope this concept was easy to understand, and for some people it might seem a little elementary, but to revise this and to really hold this concept in your head and to to write it down on your own. So what you should do is you should watch this video, and then you should first make sure that you've absorbed the contents quite well. Maybe you can watch the video twice, and you can go back to the points that you sort of missed or you thought were kind of important, and then you should sit down and try to write down all the definitions and come up with all the situations that I've detailed on your own. With a piece of paper and a pen, you should try to come up with all the theory and all the situations, and maybe check it with examples that you've seen in the past, to convince yourself. And this is the way to remember it for the future. This is the way to sort of cement the concepts in your head. So hopefully you enjoyed the video. Until next time, this is goodbye from my side.